Hi guys, क्या हाल चाल है भाई? Hello everybody, good morning, good morning. I was just trying to fiddle with something and this my face came on the camera. Anyways, how are you guys doing? How are you guys doing? Good morning, good morning. It's lovely to see you guys over here so early in the morning, and there's a bit of a change in the schedule, uh, which I'll talk a little later. Last class you missed. Yeah, you missed the last class, but I guess the last class recordings are already there on the YouTube. And so you can watch it as and when you want. So there is a small bit of a change. Earlier, until Pahul sir was not here, so I used to take classes on from Monday to Friday. But since he has come back, I'll be taking classes on Monday, Wednesday, and Friday. Okay, I'll be taking classes 3 days. Uh, I'll be taking classes 3 days a week on Monday, Wednesday, and Friday. The timings would be the same, like 9:30 to 10:30 for 12th standard kids, and 10:30 to 11:30 for 12th standard. Sorry, 9:30 to 10:30 for 12th standard kids, and 10:30 to 11:30 for 11th standard kids. Okay. So good to see you guys over here, and we are currently doing coordination compounds. We are almost like nearing the end of coordination compound. Like today we would be discussing valence bond theory, and in the next class we'll be discussing isomerism. Okay, so chalo, let's start today's discussion without any delay. And today's discussion revolves around valence bond theory. Now, before I go ahead and start with the discussion, okay, before I go ahead and start with the discussion around valence bond theory, let me just tell you about the problem that we had taken in the last class. The problem that we had taken in the last class was that if there is a tetrahedral complex which is getting formed, then you had to tell me the angle at which the ligand and the d orbitals are present. As we had discussed that in a tetrahedral complex, the splitting is entirely different, as in like 4 ligands approach the d orbitals from the corners of a cube, alternate corners of a cube, rather than they approach them from the axes. Okay, so you had to tell me that what is the angle between the ligands and the d orbitals which are present in the central metal atom. More so, you had to identify how do you get these angles. Okay, so the question was like this, that if there is dx square minus y square and dz square, what is its angle with respect to the ligand? And if you take dxy, dxz and dyz with respect to the ligand, then what is the angle? I'm fine, thank you, Aviraj. I'm just on the road to recovery. So anyways, as we had discussed earlier, that the splitting is different, as in like the T2G set of orbitals which are there for octahedral. T2G set was having 3 d orbitals, dxy, dxz, dyz, will be raised in energy while the orbitals Eg, that which contained d x square minus y square and dz square, will have a decrease in their energy. The reason that was given was that the angles of these ligands with respect to the T2G set and the Eg set are different. The T2G set is at a smaller angle and the Eg set is at a larger angle. In fact, the angle of the metal ligand in Eg orbital is 1/2 of the tetrahedral angle. If you look at this angle, this is a tetrahedral angle, and so the ligand is present on the axes, and it is half of this whole angle, the angle between L1 and L2 or L4 and L3, this angle is 109 degree 28 minutes. So the angle between L4 and dz square is half of this, that is 54.44 degrees. Okay, 54 degrees and 44 minutes. 54 degrees and 44 minutes. But if I look at the orbitals which are present between the axes, they are present at an angle of 35 degrees 16 minutes. It's 1/3 of the tetrahedral angle. So these are present at an angle of, this theta between them is 54 degrees 44 minutes, and the theta between them is 35 degrees 60 minutes, and the only person who was able to give this answer correctly was Muralidhar Das. Good, congratulations Muralidhar. Sorry, Abhiru. Sorry, I guess Muralidhar is a different person. Abhiru comes from Raghunathpur, Purulia, and he has predicted correctly that the angle between the axial d orbitals and the ligands is around 55 degrees, and between the ligands and the non-axial d orbitals is 35 degrees. When will you take classes in studio board? When my house is a little tiny, so I do not have a lot of space to have that whiteboard arrangement. Okay, you have to tolerate me like this. Once I get to have a bigger house, then maybe I'll be able to take classes in that studio environment, or if I do go to take classes from the Vedantu office, maybe then. Acha. Okay. So, let's start with the valence bond theory. Now we have read few bonding theories, or few theories which explain how bonding takes place, and we have discussed them in detail. Like we have discussed Werner theory of coordination compounds, we have discussed effective atomic number, we have just finished crystal field theory. Okay, and what is valence bond theory? Valence bond theory is a different kind of a theory. Valence bond theory tries to predict the hybridization of a central metal atom when it is forming bonds with certain ligands. Now, how do we identify, how do we use valence bond theory? Now remember, this valence bond theory, you might have seen this valence bond theory in the topic of bonding as well. Chemical bonding में भी ये था. Okay, this was also present in chemical bonding. So in chemical bonding as well, this particular concept was there. Also, we had read in chemical bonding the formation of CH4. Okay, the formation of CH4 using valence bond theory. Valence bond theory was a theory proposed by, you can say, Linus Pauling. And let's try to apply valence bond theory to complexes. But before we go to apply valence bond theory to complexes, let's revise what valence bond theory in respect to what we had read in chemical bonding. So just give me a moment. So in chemical bonding we had read that if suppose we have a carbon atom and I have to form a CH4 molecule. Okay, if suppose we have a carbon atom and we have to form a CH4 molecules. So there is a carbon atom and it has to form a CH4 molecule. Now what we had read in valence bond theory in chemical bonding, that carbon's configuration is 1s2, 2s2 and 2p2, which results in the valence shell to have two orbitals which have unpaired electrons and one orbital which is vacant. Now valence bond theory says that the number of bonds which are to be formed should be equal to the number of orbitals which have unpaired electrons. I hope you know this. The number of bonds which are to be formed should be equal to the number of orbitals which have unpaired electrons. So I need to form 4 bonds. मुझे bonds कितने बनाने हैं CH4 में? I need to form 4 bonds. So that means I need to have 4 orbitals with unpaired electrons. And so carbon in excited state, this was carbon in ground state, will have a configuration like this: 1s2, 1s2, 2s1, 2p3, which will look like this. So you can say that this electron gets excited to this level, and now we have, now we have 4 orbitals with 4 unpaired electrons. Good. We have to form 4 bonds, so we have 4 orbitals with 4 unpaired electrons, and then all of them will undergo a process known as hybridization. All of them will undergo a process known as hybridization. All of these orbitals which have unpaired electrons will undergo hybridization. So this will undergo hybridization, this will undergo hybridization, and if they undergo hybridization, they will generate orbitals which are these. They will generate 4 hybrid orbitals, and for each hybrid orbital will have a nature sp3. So 4 sp3 hybrid orbitals, and these hybrid orbitals will now combine with hydrogen, receive 1 electron or share 1 electron and form a CH4 molecule. Okay, I hope there is no problem in this one because you have already read this. However, the moment we extrapolate this to, when we extrapolate this to a metal complex, so उसमें क्या होता है that we have to consider in a metal complex that number of hybrid orbitals So first and foremost, you have to remember that ligand donates 2 electrons. Each ligand, each donor site will donate 2 electrons, and so rather than requiring a orbital with a single electron, can you see that we had required orbitals with 1 electron each? So unpaired electrons had to be present in each of these orbitals. Unpaired electrons had to be present in each of these orbitals. Rather than having these unpaired electrons, the orbital have to be vacant. So यहाँ पे rule थोड़ा change हो जाता है, a bit of a change, that number of bonds formed with ligand should be equal to number of vacant orbitals. So we need to have, now if I have to form 6 bonds, for example CuNH3 6, if I have to form 6 bonds, or K4FeCN6, so Fe is forming 6 bonds with the ligands. If it is forming 6 bonds with ligands, then I need 6 vacant orbitals in which electrons can be received. Okay. So the central metal atom has a number of empty orbitals for accommodating electrons donated by ligands. Okay. The formation of complexes involves a reaction between this Lewis base and Lewis acid. So ligand donates 2 electrons and metal receives them. So what is the metal? Metal is the central metal. It receives the electrons. Metal behaves as a Lewis acid and the ligand behaves as a Lewis base. Now whatsoever be the number of vacant orbitals, they will undergo hybridization and generate equal number of hybrid orbitals which will receive electrons. So the model utilizes hybridization. The model utilizes hybridization of N-1, D, NS and P, or NS and P and D orbitals to set equivalent number of orbitals with definite geometry such as octahedral, tetrahedral, square planar. The number of unpaired electrons is measured by magnetic moment, and it determines which orbitals are used. How do we determine which orbitals are used? Is by calculating the magnetic moment of the complex, the metal in the complex. Okay, let's look at certain examples, and then we can you'll be able to understand that how to apply these concepts. Okay, कुछ एक चीज़ें they are very vital, or they are like very elementary. If the number of d orbitals which are undergoing hybridization, or if the number of d orbitals which are becoming vacant is equal to 4, then the type of hybridization will be sp3. If it is becoming 4, it can also be dsp2. So coordination number 4 can become dsp3 or dsp2, can acquire sp3 or dsp2 hybridization. Coordination number 6 involves sp3d2 or d2sp3 hybridization. We focus, for as far as JEE is concerned or NEET is concerned, we focus only on, okay, focus only on coordination number 4 and coordination number 6. Okay, coordination number 4 and coordination number 6. Let's try to take an example. एक छोटा सा example लेते हैं, उससे समझते हैं. Suppose I have to predict what is the hybridization in this complex. Suppose Fe H2O okay, I have to identify what is the hybridization of iron in FeH2O6 3+. How do I make that prediction? First and foremost, you have to identify that what is the coordination number of iron. So what is the coordination number of iron? Please tell me, what is the coordination number of iron? Coordination number of iron is what? कितना है बताइए? What do you think is the coordination number of iron? Iron is forming a H2O aqua complex, and this aqua complex has 6 H2O units. So what is the coordination number of iron? Please tell me in the comment section. It is 6. Yes, coordination number of iron is 6. So can I say that the number of vacant orbitals required will also be 6? Required for receiving electrons will also be 6. Can I say that the number, if the coordination number is 6, the number of vacant orbitals required for receiving the electrons will also be 6. Okay. Now iron in ground state has 26 electrons and it's a valence shell. Valence shell in D or D block elements is the n-1, that's a d orbital and ns orbital. So it is 3d6 4s2. Okay, 3d6 4s2. Fe3 plus configuration will be 3d5 4s0. Can I say that? It is 3d5 4s0. You have removed 3 electrons from 4s and then from 3d. Okay, so first electrons will be removed from 4s and then we'll be removing electrons from 3d. So it is Fe3 plus, so I'll do it like this. Now, can I say that the electrons look like this? So this is 3d5. 1, 2, 3, 4, 5. This is 4s and 4p is vacant. 3d, 4s, 4p. Okay, 3d, 4s and 4p. Now tell me something. What kind of a ligand is H2O? What kind of a ligand is H2O? Can I say H2O is a weak field ligand? H2O is a weak field ligand. It's a weak field ligand. Yep, H2O is a weak field ligand and it is an octahedral complex. So if I remember correctly, the d orbital is splitting in an octahedral geometry, then can we say that if we have a d5 configuration, d5 configuration will split in this form? D5 configuration and will split in this form, and d5 in a weak field will be arranged like this. D5 in weak field will be arranged like this, that is T2G3 Eg2. Can you see any pairing of electrons taking place over here? Can you see any pairing of electrons? कुछ pairing हो रहा है यहाँ पे? There is no pairing of electrons. All electrons are remaining unpaired. That means these electrons over here in 3d orbital will also not undergo pairing. You will not perform pairing. So no pairing will take place. So the number of times pairing will occur will correspond to what extent pairing was taking place in crystal field theory. If there was no pairing occurring in crystal field splitting, then you will not pair any electron in valence bond theory. If pairing was occurring, then you will go ahead and pair these electrons. So remember, this is why crystal field theory was studied before valence bond theory, so that you understand whether pairing will take place or pairing will not take place. Since it is weak field ligand, so no pairing will occur and we will leave the d orbitals as it is. So अब ये d orbitals ऐसे ही रह गए. We need how many vacant orbitals? We need 6 vacant orbitals. So I have a vacant orbital over here and 3 vacant orbitals over here. So I have a total of 4 vacant orbitals. I need 2 more. So what I will do is I will utilize 4s, 4p and 4d orbital, and among 4s, 4p and 4d orbital I will be utilizing, can you see which orbitals have I utilized? I have utilized 1s VBT was given before CFT, but CFT gives a better explanation gives a better explanation of how electrons are arranged rather than VBT. Okay, so we will be hybridizing these orbitals. Kitne orbitals? 1, 2, 3, 4, 5, 6 to generate 6 sp3d2 hybrid orbitals, and they will receive electrons. These hybrid orbitals will receive electrons from the ligands. They will receive electrons from ligands. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 12. Okay. You will receive electrons from H2O in these hybridized orbital, and so our hybridization turns out to be sp3d2. sp3d2 hybridization. Is that understood? I hope you have understood this. The method is pretty simple. You take a metal, remove relevant number of electrons, as many as per the oxidation state, and then check whether the electrons will undergo pairing or will not undergo pairing. A good way to check it in the octahedral complex is to see whether in the octahedral field and with that given ligand, electrons will undergo pairing or not undergo pairing. With a strong field ligand, electrons should undergo pairing. With a weak field ligand, electron would not undergo pairing. However, it is not always true that all electrons will undergo pairing. Please do remember, all electrons would not undergo pairing. Pairing will depend, the extent of pairing will depend on whether all electrons could be paired in the crystal field theory or not. Whatsoever number of electrons are paired in crystal field theory will be paired over here in valence bond theory. Okay, I hope this is clear. So let's take some more examples. Okay, and before we take some examples, let's take a question. For the correct assessment of electronic configuration of a complex, the valence bond theory often requires the measurement of which of these properties? Is it molar conductance? Is it optical activity? Is it magnetic moment, or is it dipole moment? Which of these properties need to be identified so as to get a fair idea about which orbitals are involved in hybridization? The right answer is C. Very good, Akanksha. Very good, Vijay Kiran. The right answer is magnetic moment. What does magnetic moment do? Magnetic moment tells us whether there is any pairing or unpairing, or if there is unpairing, then how many electrons are left unpaired, or if there is pairing, then how many electrons are being paired and how many electrons are being left unpaired. Okay, so the right answer should be magnetic moment. This was already discussed as one of the features of valence bond theory. So valence bond theory has to be supported with magnetic moment so as to make the most appropriate conclusion. Okay, so let's start with coordination number 6. And in coordination number 6, we had discussed that it looks like this. This is octahedral. This is octahedral geometry. Okay, and you can have the hybridization as sp3d2 or d2sp3. Okay, sp3d2 is known as the outer orbital complex because the outer nth d orbital is used, and n-1 d orbital if is used, it is known as the inner orbital complex. So let's take a question which is CuNH3 6 3+. Let's try and understand this. Let me just tell you the method first, and then we can go by whatever is written over here. So CONH3 6 3 plus. Okay, पहले तो ये बताओ कि what is the coordination number of cobalt? Cobalt's coordination number is C5H5 bidentate है क्या विघ्नेश्वर मिश्रा? C5H5 bidentate, ऑर्गेनिक लाइगेंड्स में हम बाइडेंटेट और मोनोडेंटेट हम नहीं बोलते हैं, उनके लिए एक डिफरेंट वर्ड यूज होती है जिसको बोलता है हैप्टिसिटी. ओके, सो द कोऑर्डिनेशन नंबर इज 6. Okay, coordination number is 6, and the oxidation state of CO is +3. Also, nature of ligand. What is the nature of ligand? The ligand NH3 behaves as a strong field ligand. NH3 behaves as a strong field ligand. We have to just identify whether it behaves as a strong field ligand or a weak field ligand. That is our job. So first and foremost, I'll write CO 3 plus as configuration. CO cobalt atomic number is 27. So CO 3 plus will become 24, and this 24 will be written as 3D. So this is 3D6, 3D7, 4S2. So it will be written as 3D6, 4S0. 3D6, 4S0. Okay, 3D6, 4S0. Now, if I look at the arrangement of electrons in 3D6, it will be written like this: 2, 3, 4. 1, 2, 3, 4, 5, 6. And this will be S orbital, this will be P orbital. So this is 3D, this is 4S, and this is 4P. Now please tell me something, that if I have a D6 configuration in a strong field, how would the splitting look like? D6 in a strong field ligand environment will look like this. Just a moment. One, 2, 3, 4, 5, 6. अगर D6 को हमने लिख लिया है, if it is written D6 in a strong field case and it is octahedral complex, so it will be written as T2G6EG0. That means D6 configuration was in this form: 1, 2, 3, 4, 5, 6. All the d orbitals are occupied, but in the strong field case, what will happen is 2 d orbitals will become vacant. So CO3 plus NH3 will generate, CO3 plus NH3 will generate the arrangement like this. One, 2, 3, 4, 5, 6. And your 2d orbitals will become vacant. Okay, your 2d orbitals will become vacant. Now what will happen is the d orbitals which are becoming vacant, they will undergo hybridization. These two, D2sp3, so they will undergo hybridization to form D2sp3 hybrid orbitals, which will now receive electrons. Okay, which will now receive electrons. Now over here, can you see that they have drawn certain arrows, these dotted lines? देखो यहाँ पे dotted lines कुछ बनाया है इन्होंने. Okay, it is always a little misleading to identify that how many electrons will get paired by using VBT. So we use the help of crystal field theory to predict how many electrons will get paired. Okay, is that clear? Okay, Gurjot. Okay, so is that clear? I hope you have understood how did we arrive at the hybridization. So let's, if I have to identify what is the magnetic moment, since all the electrons are paired, I will call it a diamagnetic species. Okay, diamagnetic species. So can you see this? D2sp3 hybridization of CO3 plus. D2sp3 hybridization of CO3 plus. It's a pretty easy concept, provided you do not panic. You just do not try to memorize the stuff. You try to utilize CFT to predict how, to what extent the electrons will get paired, and then utilize this feature in valence bond theory. Okay, is that clear? I hope this is clear. Chalo, let's take another question. COF6 3 minus. COF6 3 minus. So this should be easy. COF6 3 minus. First three things that we have to identify, that is coordination number of metal, which is 6. Oxidation state of metal, which is +3, and nature of ligand. So ligand is F minus, and F minus behaves as a weak field ligand. Okay, F minus will behave as a weak field ligand. So this is D6. This is CO3 plus. We just figured out that CO3 plus will be in D6 configuration. D6 configuration, if in weak field environment, then what will be the arrangement of electrons? D6 in a weak field environment will be arranged like this. I'll write, sorry, T2G4 Eg2. How would I write this? T2G4 Eg2. This we have already discussed earlier in crystal field theory, that what will be the relevant configuration in the T2G Eg notation. So please do watch that video. So it will be, because these are d orbital electrons, 1 2 3 4 5 6, and when splitting takes place, 1 2 3 4 5 6. So we will have a configuration like this, T2G4 Eg2. Yep. So T2G4 Eg2 होने का मतलब, are we leaving any d orbital vacant? Are we leaving any d orbital vacant? Are we leaving any 3d orbital vacant? Any orbitals vacant? बताइए, are we leaving any d orbital vacant in the field of fluoride ions in CO3 plus? Are we leaving any d orbital vacant? Absolutely not. Answer is no. We are not leaving any d orbital vacant. So we need we need 6 orbitals which are vacant, since n-1th. Why it is known as n-1th? Because this is 4s, so this will become n-1 3d. Any d orbital from n-1th will be not utilized, and what we will utilize is 4s, 4p, and 2 d orbitals from 4d. So the hybridization for this molecule COF6 3- should be sp3d2. sp3d2 होना चाहिए. Clear? It should be sp3d2. Since none of the n-1 and d are utilized, हमें 6 utilize करना है. 6 is needed. So 4s, 1 4s, 3 4p, and you will utilize 2 d orbitals which are present in 4d valence shell. sp3d2. Yep. So let's see if we have done it correctly or not. Yep. sp3, this should be sp3d2. Okay. sp3d2. Can you see this? This is 4s. These 3 are 4p. And these 2 are 4d. 4s, 4p, 4d. Yep. Clear? I hope this is understood. Okay? We can extrapolate this idea to tetrahedral complexes as well. Let's go on to tetrahedral complexes. But before that, let's try to solve this question. Now, before this question, please tell me how many unpaired electrons were present in CuF6 3-. The number of unpaired electrons present in this. Number of unpaired electrons present in this is 4. And so if you are being asked that what is the spin magnetic moment, mu will be equal to root over n times n plus 2 Bohr magneton. So Bm. So n is the number of unpaired electrons. So 4 times 6 Bm, that is root 24. Okay. So that root 24 will be 4 times 6 and it will be 2 root 6 Bm. 2 root 6 Bm. Okay. So the magnetic moment of this complex is 2 root 6 Bm. If all the electrons are paired, then the magnetic moment will definitely become equal to 0 because there will not be any unpaired electrons. Okay. So let's try to take this question. Which of the following is a high spin complex? Which of the following is a high spin complex? Please look at the question and then answer it correctly. The right answer for this question will be FeF6 3-. Quite obvious because NH3 has a strong field ligand, Cn is a strong field ligand, and fluoride is a weak field ligand. So in fluoride, chances of the metal to have larger number of electrons which are unpaired is pretty high. The right answer should be D. Which of the following complexes will be an outer orbital complex? Which of the following complexes will be an outer orbital complex? Now this will require a bit of calculation. Okay, a bit of calculation. CuNH3 FeCl6 4-. Let's look at them first. So CuNH3 FeCl6. So CuNH3 we have already identified that it is D2sp3. Now FeCl6 4-. In FeCl6 4-, you have Fe2 plus configuration, that is 3d6 4s0, and 3d6 in a strong field plus strong field will become T2G6 EG0. So D6 configuration in a strong field will become T2G6 EG0. Okay. T2G6 EG0. Now in T2G6 EG0 there will be two d orbitals which will be vacant. And which d orbitals are vacant? The inner d orbitals. So can I say that inner d orbitals vacant? Okay, so the hybridization for this will turn out to be D2sp3 again. MnCN6. So Mn 2 plus will be having 3d4 4s0 configuration. 3d4 4s0 configuration. Now d4 in a strong field will arrange itself like T2G4 EG0, inner d orbital vacant. So the hybridization will again turn out to be D2sp3, which leaves me the last one, that is Ni2 plus. Ni2 plus will be 3d8 4s0. Okay, 3d8 4s0 present in a strong field. So 3d8 D8 configuration in a strong field arrangement will be T2G6 EG2. None of the d orbitals are vacant. No d orbital vacant, and therefore we need to use the outer orbital or the nth d orbital. So in this case we are utilizing n minus 1th d orbital. This is n minus 1th d orbital. But in this case we will be utilizing nth d orbital because the inner d orbitals are no longer vacant. The right answer will turn out to be D. The right answer will turn out to be D. It's a very beautiful question. You have to remember few things before you go ahead and solve this. Okay, you need to be proficient in arranging electrons in the T2G-EG configuration so as to identify whether the electrons are undergoing pairing or not. Okay? The right answer will be D. Clear? So next, how many unpaired electrons are present in Fe(F6) 3- complex ion? So Fe is +3, fluoride is weak field. So number of unpaired electrons present in Fe(F6). Space Explorer, are you free? We didn't see you for last 2 days for our test discussion. And who are you? Test discussion, you are in which batch? How many unpaired electrons are present in Fe(F6) 3- complex? The right answer will turn out to be 5. Yep, we have solved this question just in this very class. Okay, answer should be 5. The next one is the number of unpaired electrons in D6 low spin octahedral complex. Arey man, the toppers class batch were, the discussion session was on Monday. Monday was the Shara. So the discussion will take to some other day. Okay. The number of unpaired electrons in D6 low spin octahedral complex. Now the meaning of low spin means strong field ligand is present. So if there is D6 plus a strong field ligand which is present, it will be T2G6 EG0. Okay, the right answer will be D. Answer should be D. Okay, answer will be D. It will have no unpaired electrons because it is written low spin. Now low does not always mean zero. Low could be anything which is different from a weak field ligand, okay, which is lesser than a weak field ligand. Now in case of a strong field ligand, to what extent? In case of a weak strong field ligand, to what extent the electrons will be paired will depend on how many electrons are present in d orbital. So 6 electrons completely paired, and so we will have no unpaired electrons, so the right answer should be 0. We can utilize it for coordination number 4, and for coordination number 4 you are given 3 very common examples: NiCl4 2-, NiCO4, and then NiCN4 2-. You have to just remember, okay? भाई क्यूबर पियानिस्ट, इफ केमिस्ट्री पढ़ने का मन नहीं कर रहा है भाई, मत पढ़ो, कुछ और पढ़ लो. So this is a weak field ligand. CO is a strong field ligand. CN is a strong field ligand. We have to utilize the same process to estimate what will happen. So if I take NiCl4, NiCl4 2-, then we have coordination number 4, oxidation state is 2 + 2, and ligand is weak field ligand. Okay, Sir Crystal Vigneshwar Mishra asks, Sir, crystal field से और valence bond theory से strong field ligand same होते हैं. भाई strong field ligands को ये थोड़ी पता है कि आप कौन सी थ्योरी उन पे लगा रहे हो, तो वो हमेशा strong field ligand ही रहेंगे. Strong field ligands do not know that which theory you are applying on them, so they'll continue to be strong field ligands irrespective of the theory that you are utilizing them for. Okay. Okay, now we have Ni2+. Ni2+ will be 3D8 4s0 configuration. Okay, 3D8 4s0 configuration. So 3D8 will be like this. In a weak field environment, 3D8 okay, in a weak field environment, 3D8 configuration will remain as it is, and thus we will utilize 4s and 4p. You can also try to do it in terms of coordination number 4 splitting or crystal field splitting in 4 coordination number. So 3D8 will look as if EG4, sorry, just a moment, it will look like this. So lower energy set is the EG, the higher energy set is the T2G. G नहीं लगाते, E लगाते, and so E4 and T2, 4 electrons will be there. So there are these two. You will put 4 electrons over here, and 1, 2, 3, 4. So there will be two unpaired electrons which will be left out even after splitting of d orbitals in a weak field scenario. So what we would do is we will have to utilize 4 unfilled orbitals. So we will utilize S and P, 4s and 4p. So NiCO4 will turn out to be sp3 hybridized. In this case, we shall call the tetrahedral ones outer. Yes, correct. Tetrahedral S. If the hybridization turns out to be sp3, then it is outer orbital complex. And if the hybridization would have turned out to be dsp2, then we would have called it inner orbital complex. Okay. So can you see sp3 for Ni2 plus. Okay, sp3 for Ni2 plus. So this is the homework question for you guys, that you have to predict correctly the hybridization of nickel in NiCO4. What is the hybridization for this? And what is the hybridization for nickel in NiCN4 2-? Okay, the hybridization of nickel in NiCO4, nickel in NiCN4. Okay, this is the homework question. Please do give your answers in the comment section. Also, it would be lovely if you do show, if you tell your work, if you describe your work, so I will be more convinced. It will sound to be more convincing. And so with that, we end today's session. And in the next session that will take place on Friday, we will start with isomerism. Okay, we'll do structural and then we'll do a bit of stereoisomerism. Okay, so chalo, all the very best guys. Keep yourselves safe and keep yourselves healthy. And please do join me on Friday on the same Catalysis channel of Vedantu for discussion around the isomerism that is being shown by these complexes. Okay, so हमने काफी comprehensively पूरे coordination compounds को पढ़ा है. If you go through all the videos, you can also take help of them to solve questions. Okay. Bye bye guys, have a lovely time. Let's meet in the next session.